Okay, so now we're going to talk about ways that we measure the heat exchanges that we've been talking about in previous conversations. And one really valuable method for us is calorimetry. Calorimetry is used to measure the amount of heat transferred to or from a substance. Okay, so the heat exchanged with the calibrated object, the heat is exchanged with the calibrated object, which we're calling a calorimeter, which we'll define in a couple slides. The change in temperature of the measuring part of the calorimeter is converted to heat. All right, so we need a couple of the terms to sort of help identify everything or help sort of clarify everything or stick things in boxes. First of all, the system. The system is a substance or substances undergoing the change. It's oftentimes a chemical reaction. And the surroundings is oftentimes the calorimeter, right? It's the other components of the apparatus that serve to either provide heat to or absorb heat from the system itself. All right, so the calorimeter is the device that we're talking about that we use in calorimetry. It's used to measure the amount of heat involved, and many processes that happen in a calorimeter happen in solution. If the reaction is exothermic, then the heat is produced by the reaction and is absorbed by the solution. If the reaction is endothermic, then the solution provides the heat that's needed for the reaction. Okay, so here's a couple graphics of some calorimeters. And exothermic, so you've got some system in here, some reaction happening inside this water. Okay, so if it's exothermic, then heat, right? There's our little Q. He's going to be flowing out of the reaction into the surroundings, right? And so in time, the solution heats up and the temperature goes up, and that's how this works, okay? Now, if the system is endothermic, then heat is going to come from the water or the solution into the reaction, right? And it's going to cause the temperature to drop. All right, so there's a couple good graphics of calorimeters. A calorimeter must be well insulated in order to prevent transfer of heat with the outside environment, of course, because we don't want the heat, to be going off into the room where we can't measure it, right? We want it to be going into the calorimeter where we can measure it. To obtain accurate results, all heat exchange must take place only between the system and the surroundings, right? I mean, obviously, we can never get that perfect, but the closer we can get to all, the better off we are. So, coffee cup calorimeters, oftentimes used in Gen Chem labs, they're composed of coffee cups. And there's other kind of calorimeters which are more expensive, commercial calorimeters, better designed, and they're used for industry and research. But here's a couple graphics here. A coffee cup calorimeter, can you just see two coffee cups right here? There's a coffee cup here, another coffee cup, and there's a cover. So the double coffee cup means that it's super well insulated, not super, but pretty well insulated, right? And you might have a hole in the cover, and then a stir, which you sort of drop up and down. Can you see that loop? It's going to stir everything, okay? Another hole for the thermometer. Then you've got some reaction going on inside there. And when you see the temperature go up or down, then you've measured your stuff. This is a coffee cup calorimeter, super inexpensive, super simple to make up, and we still get reasonably good results. So some more expensive apparatus. This one looks a lot like the coffee cup calorimeter. You've got a nice simple one here, and you get a metal outside vessel, another metal inside vessel, and the air in between is going to be the insulator, right? You're going to have air in between it. When you drop this down in here, it's going to be just a bunch of air. Going to insulate that real nicely. You stir, might have a similar stir to the coffee cup calorimeter and a thermometer, right? So this looks a lot like the very inexpensive one that we saw in the previous slide. A more expensive and more precise one might have a little motor in it, right? There's a motor which turns this stir around a lot. You've got a really precise thermometer, right? So you can have different kinds of calorimeters with different levels of sophistication. But in general, calorimetry, super, super useful and oftentimes very, very precise. So here's a couple principles that we need to consider. Suppose you take a hot piece of metal and cold water, M and W, right? If the metal is placed within the water, then of course it's going to heat the water up, right? The temperature of the metal is going to go down. The temperature of the water is going to increase, right? And eventually, they're going to be the same temperature, which we're going to call thermal equilibrium. All right. So, since this is done in a calorimeter, the heat is exchanged only between the metal and the water. The net change of the heat is zero, right? So we're going to say whatever the heat whatever the metal loses, the water is going to gain, right? We might say that. Now, rearranging, oops, I don't have that equation here. Skip that. Let's look at that here. The heat of both substances is equal in magnitude, but opposite in sign. Okay, we'll give more details on that in just a minute. And you know what? I can do that now. Let's do this. Q is equal to M, or rather, let's say this is the Q of the heat for the metal and the heat of the water. This is going to be Q MC delta T, right? That's how much the MC delta T. That's how much the metal loses, MC delta T. And here is how much the water gains in heat, right? So this is the mass of the metal, of course. Here's the mass of the metal, the heat capacity of the metal, and the change in temperature of the metal, right? And here's the mass of the water and the heat capacity of the water and the temperature change of the water, right? So the net change is 0. So in other words, what goes into one comes from the other, right? And so that's why these are equal in sign. We'll do one of these in just a minute, so hold on to your hats. So in the simple calorimetry process, here's the metal we were talking about a minute ago. The metal, suppose it's really hot. The heat's going to be coming out of the metal into the water, and the water's going to heat up, right? And the water's what's being measured here. Can you see the temperature goes up? And the temperature of the metal is going to go down. So let's look at this example here. It's a little bit elaborate, but I'm going to see if I can get this all in this one slide. I'm going to have a metal and water, okay? And the mass, we'll do this in grams. The mass of rebar, a steel rod used for reinforcing concrete, is 360 grams. 360 grams is dropped into 425 mils of water, right? And we know that if the volume of water is 425 mils, its density of water is equal to 1 gram per mil. So its mass of water is going to be 425 grams, right? So that'll be 425 grams of water. And the water is initially, let's go back to here, T1 is equal to 24 degrees centigrade. No. Yeah, that's right. Water at 24 degrees centigrade. And the final temperature, T2, is equal to 42. I need black. I'm trying to keep these markers nice, okay? 42.7 degrees centigrade, 42.7, and delta T now. I didn't leave myself nearly enough space for this. You know, I'm not going to finish this problem. I'm going to do this on request. 42.7, delta T is a question. We don't know the delta T there, but we do know the delta T here. It looks like it's, what is that, 16.7? No, 18.7? 18.7 degrees, right? Final minus initial, that's 18.7 degrees centigrade. Okay. Calculate the initial temperature of the piece of rebar. So I'm going to set the equation up for you, but I'm not going to do it because I want to save time and I don't want to spend, I'm going to save time. I'm going to do it. Let's do this in blue. We know that the heat that the metal lost, right, of the metal is equal to positive heat of the water, right? So this is going to go mass of the metal, specific heat of the metal. It's steel. We've got to look that up. Table 5. We're going to use iron. Okay? So MC delta T is equal to MC delta T of the water, right? This is the water here. And this is the metal. The mass of the metal and the specific heat of the metal and the temperature of the metal, okay? So, and you know that you also know that that delta T is T2 minus T1, right? So with this information alone, you can solve this equation. But watch out now. What was lost by the metal was gained by the water, okay? So I'm not going to solve that. There's the equation for it. I showed you how to set it up, but I'm not going to, as I said, I'm not going to solve it. So we may do that together in class.